In part 1 of our lesson on character arrays and pointers, we saw how we can store strings in character arrays, and we also saw how we can work with character arrays using pointers in some of the basic scenarios. Whenever we are working with pointers, it's really important that we visualize how things are happening in the memory. So the first thing that we will do in this lesson is we will simulate the program that we had written in the previous lesson to print the characters of a string and see what goes where in the memory. And we will also look into the concept of string constants and constant pointers. So this is where we had left in our previous lesson. We have written a function print to print the characters in a string. In the main method we have a character array of size 20, but we have stored a string of length 5 in it. We have used a string literal, so null termination is implicit. We have talked about this earlier. So let us step through this code and see how it is working. Once again, I have drawn this familiar diagram. The memory that is allocated for execution of a program is typically divided into these 4 parts, these 4 sections. One part of the memory stores the instructions in the program. We call that the code segment or the text segment. One section stores the global variables, and stack is where all the information regarding function call execution and all the local variables go. Whenever we are writing a program, whenever we are executing a program, we should always visualize what variable goes where, or what data goes where, and what is the scope of that variable or data. Okay, so let us run through this code and see what is happening in the memory. When this program will start executing, first the main function will be invoked. Whenever a function is called, some amount of memory from the stack is allocated for the execution of that function. It's called the stack frame of that function. So let us say this stack frame from address 100 to 150 is allocated for the main function. Stack is one contiguous block of memory. So let us say in the stack the memory increases from bottom to top. All the local variables of a function go into the stack frame of the function. So when we declare a character array, 20 bytes from this stack frame will be allocated for this particular character array. Let's say they are allocated from address 100 to 120. Each character is stored in 1 byte, so we need 20 bytes for character array of size 20. Apart from local variables, there may be some more information in stack frame, so that's why we have some more space. And now the control of the program goes to this statement, print C. As soon as we make a call to another function from a function, the execution of that particular function is paused at that particular line, and the machine goes on to execute the called function. The called function is allocated stack frame on top of the calling function, so print will be allocated a stack frame on top of main function. Whatever function is at the top of this stack and at any point is executing, main will wait for this function to finish. Let's say this particular stack frame is from 150 to 170. Main is paused and print is executing right now. Now print will also have a local variable C, but this will be a pointer variable. A pointer variable takes 4 bytes of memory in a typical architecture, so this will be taking 4 bytes. So let's say starting address 154 in this stack frame, we have 4 bytes for this particular character pointer. So this C in main is actually not the same C in print. The C in main and the C in print are different. They have different scopes. We could have named this particular variable A or PTR or whatever, but all that happens when we make this particular call to print and pass this C here is that the address 100, which is the base address of the array, is passed to the print function, and the print function keeps it, stores it in a pointer variable. Sometimes it may confuse us when we are using the same local variable name in the calling function and the same argument name in the called function, but we must always understand that they are different. Okay, to run through this code further, I'll clear some space here now. I'll draw this array C outside the stack here. We have an array of size 20, but we are only showing the first 6 positions in the array from address 100 to 105, and that's why it is extending towards the right. The sixth character is a null character, and the first 5 characters are the characters of word hello. Now we have this another guy, which is C of print, which is a character pointer at address 154 that stores address 100, so it points to the first element of the array. Now let's come back to our program execution. Let's say we are here initially. I'll mark the statement that is executing by this green arrow. Let's name these two guys. This guy is C, but this guy is an array local to main, and this is also C, but it is a character pointer local to print. Okay, so now here what we are saying is, while asterisk C is not equal to the null character, when we put this asterisk operator in front of a pointer variable, we are looking at the value at that particular address. So at this stage, when C is pointing to the base address, asterisk C is H, so this condition is not true. We will go to this line printf, that will simply print asterisk C, which is H. Let's write down the output here. So we have printed H so far, and then we say C++. If we understand pointer arithmetic from our previous lessons, incrementing a pointer by 1 unit increments the address by size of the data type that the pointer points to. C here is a pointer to character data type, and character data type is 1 byte. So C plus 1, C++ is saying C is equal to C plus 1. So C now becomes 101. So now C points to the second character in the array. And once again we come to verifying this condition in the while loop. Asterisk C is E here, it's not null. Once again we will go inside the loop and print E, and we will keep on going like this till the address in this pointer variable reaches 105. Now here the value at this particular address is null character, so the loop will not execute. We will come to this statement to print an end of line, and the execution of print function will finish. So this particular stack frame for print will be cleared from the stack, will be deallocated, and now main will resume and finish. So with pointers we should always know what's going where in the memory. Okay, so let us now modify this particular code to learn some more concepts. What I'm going to do in my code is, instead of creating a character array of size 20, I'll create a character pointer named C and equate it against a string literal in a statement like this. And if you run this program, the output will be the same. What really happens is, if you use the string literal in initialization statement of an array, something like this, and then the string gets stored in the space that is allocated to the array. So in this case it will go into the stack in this character array of size 20. But if you use the string literal elsewhere in a statement like this, or maybe when we do something like passing a string literal to a function, then in these cases the string gets stored as a constant during the compile time. Most probably it will be stored in the text segment of the application memory, and it cannot be modified. So if you write a statement like this, let's say you want to change the first character of this constant string to A, running this program will give you an error, will cause a crash. Okay, coming back to having a character array. Now if we have a character array and we are passing the address of the array to a function, that function receives it in a character pointer. Now using this pointer we can modify the data in this particular array. So if I say something like this, we first change the first character to A, and then we are printing the characters, and then as you can see it is possible to do so. Now sometimes we may want a function just to read a string and not write anything. To force this kind of behavior, we can change our argument to const character pointer. Now if we run this code will give us compilation error. We can read whatever is there in the array that is passed, but we cannot write to any of the positions. This code will work fine. Pointers are really tricky, and even the most experienced programmers write buggy code when they're using pointers. I recommend that you get your hands dirty by writing some code yourself. That's the best way to learn.